Have you ever wondered just how far a human being could actually travel in the vastness of space? Not in science fiction, not in dreams, but in reality, limited by physics, biology, and the cruel arithmetic of the universe. Imagine breaking the record for the farthest distance a human has ever been from Earth, only to realize that even this achievement barely registers on the cosmic scale. On April 6th, 2026, 4 astronauts aboard NASA's Artemis 2 spacecraft travelled more than 252,000 miles from our planet, surpassing a record that had stood for over half a century. That's farther than anyone alive today has ever been. It sounds staggering. It feels monumental. But here's the truth. It's less than 1% of the distance to Mars at its closest approach. If you're someone who dreams of exploring the stars, who feels the pull of the cosmos each night as you stare up at the sky, this story is written for you. This is about your curiosity, your fascination with the infinite, and your desire to understand what is possible and what is utterly impossible for humans in space. If that resonates with you, consider hitting the like button. It helps these stories reach others who, like you, wonder about their place among the stars and find solace in the knowledge that the universe is both vast and strangely intimate. So why should you watch this video all the way through? Because in the next minutes, you will learn not just about distances and spacecraft, but about the limits of the human body, the endurance of life, and the harsh reality of the universe that no amount of ambition can bypass. You'll discover why the moon was hard but achievable, why Mars stretches human capability to the edge, and why beyond Mars lies a chasm that may never be crossed by biological humans. To understand the limits, we need context. Lunar missions like the Apollo program lasted only days. The moon is 240,000 miles away, a distance light crosses in just 1.3 seconds. Rescue is possible, abort options exist. If a spacecraft fails, humans can return to Earth within 3 days. Now, imagine Mars. Even on the most conservative mission plan, a trip there would require 7 months of coasting through interplanetary space. Communication delays range from 4 to 22 minutes each way. Radiation exposure is unavoidable. Any medical emergency becomes a problem that the crew must solve entirely on their own. And that's before factoring in the nearly 500-day surface stay required for orbital alignment before a return journey. The total mission duration reaches nearly 1,000 days, almost 3 years. From a human perspective, these numbers aren't abstract. 3 years away from Earth, in an environment with average surface temperatures of -80 degrees Fahrenheit, a 95% carbon dioxide atmosphere, and no breathable air, is a level of isolation that tests every physiological and psychological limit. Every procedure, every repair, every problem must be handled by the crew alone. The energy, the resources, and the preparation required are astronomical. And that is just Mars. Beyond it, distances grow exponentially, conditions worsen, and time stretches from years into decades. In this video, you'll follow the journey of human ambition from Earth's orbit to the outer reaches of the solar system. You'll see why Voyager 1, launched in 1977, remains humanity's farthest emissary, coasting through space for nearly 50 years, and why even at its speed, reaching the nearest star would take over 70,000 years. You'll understand why the limits of physics, the fragility of the human body, and the constraints of civilization itself converge to define an upper boundary for human travel. By the end of this video, you will see that the furthest humans could ever travel is not a distant star, not even Mars or Jupiter. It is a threshold where time, survival, speed and energy intersect, a point where desire meets the hard wall of reality. You'll realize that our reach into space is both extraordinary and infinitesimally small, a sphere containing only our sun, our planets, and the empty darkness that surrounds them. And yet, it is a journey worth understanding, because it reflects not failure, but the astonishing achievement of life that can ask the question, measure the universe, and seek meaning in a cosmos that is indifferent to our existence. You've seen how far humans have gone, just beyond the moon. But now imagine stepping into the void where survival becomes a battle with physics itself. The moon, a mere 240,000 miles away, allowed astronauts to return in days if disaster struck. Mars, in contrast, demands months of unbroken travel through space, where every system, every ounce of supply, every heartbeat is under pressure. Think about this. A round trip to Mars would last nearly 1,000 days. During that time, communication with Earth is delayed for minutes. Solar storms unleash deadly radiation, and the crew must solve every problem alone, from medical emergencies to life support failures. You might wonder, why risk it at all? The answer lies in human curiosity, the drive to reach beyond what seems possible, but the universe responds with its own rules, indifferent to ambition. If you've ever felt the urge to explore, to escape the confines of Earth, take a moment to reflect on the sheer scale of what lies ahead. The environment between planets is not just empty, it is hostile in every dimension. Radiation beyond Earth's protective magnetosphere penetrates even the thickest materials, accumulating damage that the human body cannot repair. Bones weaken, muscles atrophy, vision can degrade, and the immune system falters. A mission of months already challenges the body in ways that still surprise scientists. Now, extend that to years, or decades, and the fragility of human life becomes starkly apparent. Beyond Mars, the gas giants, Jupiter, Saturn, Uranus, Neptune, present challenges that are fundamentally different from anything humans have faced. The distances stretch into hundreds of millions or even billions of miles. Transit times expand to decades. Sunlight becomes a scarce resource, and resupply is physically impossible. The outer planets are not merely farther versions of Mars. They are worlds where time, radiation, energy and isolation converge into barriers that no human engineering has yet overcome. While robotic probes like Voyager, Juno, and Cassini traverse these realms successfully, humans are constrained by biology. Robots do not need oxygen, food, or exercise. They endure radiation that would kill a human in hours. They can coast for decades, even centuries, without psychological stress. Humans, in contrast, age, weaken, and accumulate damage with every mile travelled. Even if we could build a fusion-powered spacecraft capable of reaching a fraction of light speed, the energy required to accelerate, decelerate, and sustain life is staggering beyond any current civilization's capacity. And while concepts like generational ships or cryo-sleep offer theoretical solutions, they remain speculative at best, leaving us with a sobering reality. Our biological limits combined with physics define a horizon we cannot cross. Yet within this harsh truth lies awe. Every mile we have travelled, every robotic emissary we send extends the reach of human knowledge. The distance to the moon feels immense, but it is only a heartbeat on the cosmic scale. The distances to Mars and the outer planets dwarf human experience, but they illuminate the ingenuity required to explore even a tiny fraction of space. As you close your eyes tonight, consider the paradox. We are fragile beings confined by our biology, yet we have the intellect and curiosity to measure the stars, to send our machines into the void, and to understand a universe that stretches far beyond our grasp. This is the reality of deep space travel, the frontier where human ambition meets the immutable laws of nature, and where the limits of survival define the furthest a human could ever go. Humanity has always looked to Mars as the next frontier. a world that seems within reach yet challenges everything we know about survival and endurance. Unlike the Moon, where astronauts could return to Earth within days, Mars demands months of continuous travel, where life support, radiation shielding, food and water become constant, unyielding concerns. A mission designed with current or near-future technology would require a minimum of 7 months to reach the planet, with total mission duration, including surface stay and return, approaching 3 years. During this time, communication with Earth would be delayed from 4 to 22 minutes each way, making real-time guidance impossible. Imagine being in a medical emergency, performing a critical procedure with only your training and limited supplies, knowing that help is literally millions of miles away. The environment itself is hostile. Surface temperatures average -80 degrees Fahrenheit. The atmosphere is 95% carbon dioxide and almost nothing like Earth's, and liquid water is absent on the surface. Every system on board the spacecraft and in the habitat must work flawlessly, because failure could be fatal. Radiation is another relentless threat. Solar energetic particles and galactic cosmic rays penetrate spacecraft shielding, causing cumulative damage to DNA and increasing long-term risk of cancer, cardiovascular disease, and central nervous system disorders. Even with the thickest layers of polyethylene or water shielding, exposure cannot be eliminated, only reduced. Every additional kilogram of shielding increases fuel requirements, which in turn requires larger launches and more pre-positioned cargo flights. Logistics become a nightmare. All supplies must be launched from Earth months or even years in advance, and any failure in pre-deployed habitats or return vehicles could strand the crew with no possibility of resupply. Mars is the nearest destination where humans could plausibly survive, yet it pushes the boundaries of human capability to their limits. Life there requires careful planning, robust technology, and exceptional human resilience. Beyond the physical challenges, the psychological burden of isolation for months or years, confined to a small crew in a sealed environment, is profound. Studies simulating long-duration space missions on Earth have documented depression, sleep disruption, cognitive decline, and interpersonal conflict. The actual environment amplifies these risks, yet despite all these hurdles, Mars represents hope, a tangible objective for human exploration, a destination that tests ingenuity, endurance, and ambition. It is a world that reminds us how far humans can push against the constraints of biology and physics, a place that challenges every assumption about what is possible. Every plan, every simulation, every technology developed for Mars teaches us more about survival in extreme conditions and about the fundamental limitations of life beyond Earth. And it is within this crucible of challenges that humanity defines the outer limits of exploration, where ambition, preparation, and science converge to make the impossible imaginable. Beyond Mars lies Jupiter, the first gas giant, and the first destination where the math of human survival begins to collapse. Orbiting the Sun at 484 million miles, Jupiter represents a realm where distances, radiation, energy, and time converge to create a nearly insurmountable barrier for humans. Using conventional propulsion and favourable alignments, a trip to Jupiter would take approximately 2 years and 9 months one way. The return journey doubles that time, meaning a single mission would span over 5 years, not including surface operations, which are impossible due to the lack of a solid surface. Radiation in Jupiter's magnetosphere is extreme. Its innermost belts would deliver a lethal dose in minutes to an unshielded human. Even the Juno spacecraft, specifically designed to survive these conditions, relies on a titanium vault weighing hundreds of pounds to protect its instruments. For humans, the shielding required would be orders of magnitude heavier, increasing fuel and structural demands exponentially. The outer moons, Europa, Ganymede, Callisto, present additional challenges. Europa's ice crust is 10 to 30 kilometers thick, beneath which lies a subsurface ocean of enormous scientific interest, potentially harboring life. Yet standing on Europa's surface would expose astronauts to radiation levels hundreds of times lethal, and drilling through kilometers of ice in this environment is beyond our current technology. Any habitat would require self-sustaining life support, capable of operating without resupply for years, in sub-zero temperatures and with minimal energy available from the Sun. Titan, Saturn's largest moon, offers a slightly more forgiving environment, with a dense atmosphere and surface pressure higher than Earth's, but its average temperature of minus 290 degrees Fahrenheit and the scarcity of solar energy necessitate nuclear power and enormous infrastructure. Psychological challenges compound the physical threats. Crews isolated for years with delayed communication would face unprecedented stress, potential cognitive decline, and social strain, with no hope for rescue. While robotic missions continue to explore Jupiter and its moons, humans cannot safely operate in these environments with any technology currently available or plausibly projected. Jupiter is not just far in distance. It is a wall built from physics, biology, and logistics. A stark reminder that the limits of human travel are defined not by courage or desire, but by the immutable laws of the universe. It is here, in the shadow of the largest planet in our solar system, that we see the boundary where human exploration transforms from engineering challenge to near impossible endeavour. The lessons learned, however, are invaluable. They define the limits of survival, illuminate the hazards of deep space, and inspire every step we take closer to understanding the cosmos. Beyond Jupiter lies Saturn, a planet whose beauty masks the overwhelming challenges of human travel. Saturn orbits the Sun at nearly 886 million miles, and a conventional mission from Earth using current propulsion would require 6 to 7 years to reach the planet, one way. A round-trip mission, even with a minimal orbital stay, would span 13 to 15 years, a duration that represents a substantial fraction of a human lifespan. For a crew departing at age 35, return would occur at 50, meaning an entire decade and a half spent in isolation, without the ability to touch Earth, experience gravity naturally, or receive real-time support. During this journey, astronauts face continuous exposure to cosmic radiation that exceeds any currently safe thresholds, even with optimistic shielding. Galactic cosmic rays, highly energetic heavy nuclei, penetrate the spacecraft, damaging DNA, the central nervous system, and increasing long-term risk for cancer and cardiovascular diseases. Every year the cumulative effects grow, compounding physical deterioration. Life support systems must manage oxygen, water, and food for over a decade, with no external resupply, meaning every component must be robust, redundant, and fully reliable for the entire mission. The psychological strain mirrors the physical hazards. Isolation studies on Earth, including long-duration simulations, reveal cognitive decline, sleep disruption, and interpersonal conflicts that would intensify in real, interplanetary conditions. Communication with Earth is delayed for over an hour, making real-time guidance impossible. Any emergency must be managed internally, with limited resources and under extreme pressure. Saturn itself offers no surface to land upon. Any mission would be entirely orbital, with the crew suspended in spacecraft systems that must function continuously for decades. Titan, one of Saturn's moons, presents the only environment with a dense atmosphere, somewhat shielding radiation, and offering a nominal surface pressure for human habitation. Yet its average temperature of -290 degrees Fahrenheit demands nuclear power, immense insulation, and constant energy input. The massive required shielding, life support, and consumables increases exponentially with every added year of mission duration, compounding fuel requirements, spacecraft size, and complexity. Every problem solved reveals another, each magnified by distance and duration. Saturn illustrates the first threshold where human travel becomes not just difficult, but nearly impossible. The scale of energy, engineering, and human resilience required pushes current and foreseeable capabilities to their limits, demonstrating that beyond Mars and Jupiter, human missions transform from challenging to extraordinary exercises in survival and logistics. Yet, even within these impossibilities, we learn about the fundamental requirements of life, the fragility of human biology, and the scope of the universe that frames our ambition. The journey continues outward to Uranus and Neptune, where distances, time, and hazards converge into a barrier that humans cannot reasonably cross. Uranus orbits at roughly 1.8 billion miles, and Neptune at about 2.8 billion miles from the Sun. Transit times to these planets with current or near-future chemical or nuclear propulsion stretch beyond a decade each way, meaning a round-trip mission could span 30 years or more. A crew departing at age 30 would return around 60, having spent the entirety of their adult life in microgravity and confined space. The physical effects are profound. Chronic bone loss, muscle atrophy, cardiovascular remodeling, and vision impairment progress unchecked. The immune system weakens, making even minor infections potentially life-threatening. Renal function can deteriorate under prolonged radiation and microgravity exposure, compounding risks. Radiation exposure from cosmic rays and solar particles continues relentlessly, and even the thickest shielding adds mass, fuel requirements, and complexity. Solar energy at these distances is negligible, making solar power ineffective and necessitating nuclear reactors with their own mass, shielding, and safety concerns. Communication with Earth ranges from several hours to days round trip, removing the possibility of real-time support. Every system, from life support to habitat integrity, must function flawlessly for decades, with no opportunity for resupply or repair from Earth. The psychological burden is equally severe. Extreme isolation, delayed communication, and confinement with a small crew for decades can induce cognitive decline, sleep disruption, depression, and conflict. Uranus and Neptune demonstrate that human travel beyond Mars and Jupiter is no longer a question of engineering ingenuity alone. It is limited by biological, logistical, and temporal constraints. The outer planets serve as a stark reminder of the intersection where ambition meets physical reality. While robotic spacecraft have explored these worlds successfully, humans face a fundamentally different set of limitations. These planets mark the outer edge of feasibility for biological travelers within the solar system. The enormity of distance, the severity of radiation, and the impossibility of resupply create a boundary that cannot be crossed without breakthroughs in life support, propulsion, and biology that remain theoretical at best. Yet even as we acknowledge these boundaries, we gain insight into the scale of our universe, the fragility of life, and the extraordinary achievements humanity has already accomplished with the Moon, Mars simulations, and robotic exploration. Each step outward teaches us about survival, the physics of space, and the limits of human endurance. Beyond Neptune stretches the Kuiper Belt, a vast ring of icy bodies and dwarf planets that marks the first threshold of truly empty space in our solar system. distances here extend from roughly 30 to 55 astronomical units, where sunlight is weak, temperatures plunge to near absolute zero, and solar power is almost useless. Any mission to this region would take decades with current propulsion, exposing crews to years of microgravity, radiation, and extreme isolation. Supplies, from food and water to medical resources, must be carried entirely on board or pre-positioned, with no possibility of resupply. The psychological demands are enormous. A crew confined in a spacecraft for decades with limited social interaction and delayed communication faces risks of cognitive decline, depression, and interpersonal conflict. Radiation from cosmic rays accumulates continuously, with galactic cosmic rays delivering heavy ion damage that the human body cannot repair. Robotic probes, such as New Horizons, have successfully traversed this region, sending back invaluable data about Pluto and other distant bodies. Humans, however, cannot survive the cumulative physical and psychological stresses of a decades-long mission through the Kuiper Belt, even if propulsion technology were improved, or every increase in speed exponentially increases fuel requirements, mass, and engineering complexity. The tyranny of the rocket equation, coupled with the fragility of human biology, defines a boundary where ambition meets unyielding physical reality. Here, isolation becomes extreme. The nearest point of help is years away, and communication delays stretch into hours. Every contingency must be anticipated in advance, yet unforeseen problems could still be catastrophic. The Kuiper Belt is a quiet, cold expanse, a reminder that the solar system is far more empty than the clustered planets suggest. It is a region where exploration shifts from adventure to endurance, and the limits of human survival are starkly revealed. Here, distance is more than a number. It is a measure of exposure, a countdown of years spent in conditions that degrade the human body and mind. Despite its challenges, the Kuiper Belt holds scientific value, offering insight into the formation of the solar system, the composition of icy bodies, and the processes that govern planetary evolution. But for biological humans, it is a frontier that emphasizes constraint over conquest, a domain where our presence would be temporary at best and perilous at worst. It demonstrates that even within the solar system, there are regions that are essentially unreachable without breakthroughs in propulsion, life support, and radiation protection. Far beyond the Kuiper Belt lies the Oort Cloud, a hypothesized shell of icy bodies extending tens of thousands of astronomical units from the Sun, forming the outer boundary of the solar system's gravitational influence. While here, distances are incomprehensible. Light itself takes years to cross from one side to the other. A human mission to the Oort Cloud is not merely difficult, it is effectively impossible with any technology we can realistically project. Travel times would stretch into centuries, and the cumulative exposure to cosmic radiation would be lethal long before arrival. Life support, shielding, food, water, and energy requirements would be astronomical, and even the most robust propulsion systems would struggle to reach even a fraction of the distance within a human lifespan. Communication delays would extend to years, leaving crews entirely isolated, unable to receive guidance or assistance from Earth. Microgravity over centuries would cause irreversible skeletal, muscular, and cardiovascular degeneration. The Oort Cloud exists at the threshold where physics, biology, and engineering converge to define the outermost practical limits of human travel. Robotic spacecraft could potentially explore parts of this region over decades or centuries, but humans would be unable to survive the journey. The remoteness of the Oort Cloud, its extreme cold, and near-zero solar energy make any mission a monumental challenge, highlighting the contrast between human ambition and biological limitation. Despite this, studying the Oort Cloud is crucial for understanding the solar system's formation, cometary dynamics, and the processes that have shaped the outer reaches of our planetary neighbourhood. It serves as a conceptual boundary, the edge of the Sun's gravitational dominion, a reminder that even within our own star system, there are places forever beyond human reach. The Oort Cloud exemplifies the ultimate interplay of distance, isolation, and the fragility of human life, underscoring that our exploration is limited not by courage, but by the laws of nature that govern space, energy, and biology. Voyager 1, launched in 1977, remains the farthest human-made object from Earth, a silent emissary traversing the void of interstellar space. Travelling at roughly 38,000 miles per hour, it has spent over 45 years coasting through the solar system and beyond, powered not by ambition, but by momentum and careful engineering. By early 2026, it had reached approximately 172 astronomical units from the Sun, approaching a distance light covers in a single day. Voyager 1 has entered interstellar space, crossing the heliopause where the solar wind gives way to the interstellar medium, yet it remains deep within the Sun's gravitational influence. Every signal it sends takes over 23 hours to reach Earth, a stark reminder of the vastness that separates human civilization from the outermost reaches of our star system. Voyager's instruments endure extreme radiation, freezing temperatures, and decades of mechanical strain, yet it continues to transmit invaluable data. For humans, replicating even a fraction of this journey is impossible. Life support cannot sustain biological systems for decades. Radiation exposure, bone and muscle deterioration, and psychological strain would make survival unfeasible. Voyager demonstrates the contrast between human and robotic capability. While machines can endure and observe over centuries, so humans remain confined by biology and time. The spacecraft's trajectory offers a tangible measure of how far humanity's influence can reach through engineering, but it also highlights the limits imposed by our bodies. It is a testament to ingenuity, planning, and technology, showing that while humans may explore with curiosity and intellect, physical presence is bounded by reality. Voyager 1 continues outward, a symbol of what humans can achieve without being present, carrying golden records with images, sounds, and messages intended to represent our civilization to any distant discoverer. Its journey illustrates that even in the face of insurmountable distances, knowledge and data can travel farther than human bodies ever will, marking the edge of human reach in space while leaving the body safely on Earth. Every milestone Voyager achieves emphasizes the stark boundary between exploration and survival, between what humans can imagine and what our biology allows. It is both awe-inspiring and humbling, a reminder that the universe is vast, indifferent, and yet accessible in ways that transcend our physical limitations. Even after Voyager 1 leaves the solar system, humanity faces an interstellar chasm that dwarfs everything within the Sun's influence. The nearest star, Proxima Centauri, lies 4.24 light-years away, roughly 25 trillion miles, a distance so immense that our fastest spacecraft would require tens of thousands of years to reach it. At Voyager's current speed, a journey to Proxima Centauri would take over 73,000 years, a span of time far exceeding the existence of civilization as we know it. And propulsion technologies such as nuclear thermal or even speculative fusion drives reduce travel times to decades or a human lifetime. But each introduces new challenges: radiation exposure, life support, sustainability, energy requirements, and protection against interstellar debris. The interstellar medium, while sparse, contains enough particles that at relativistic velocities, even microscopic atoms would inflict catastrophic damage without massive shielding. communication delays stretch to years, meaning any crew would be entirely isolated, unable to receive guidance or assistance. Generational ships, designed to sustain multiple human generations, confront insurmountable ecological, social, and psychological challenges, as closed ecosystems have never operated successfully beyond a few years, and a cryosleep or suspended animation remains speculative and untested for whole humans. Even time dilation, the slowing of time at near-light speeds, offers solutions only if propulsion and energy requirements can be met, which currently exceed civilization's total output. The interstellar gap starkly illustrates that distances between stars are not incremental obstacles, but chasms that separate what is theoretically achievable from what is physically survivable. Machines can cross this void, collecting and returning data over centuries, but humans face insurmountable constraints imposed by biology, energy, and time. The gap is absolute, not in theory, but in the laws of physics, defining the true boundary of human travel. Every attempt to imagine humans journeying beyond the solar system confronts these realities, emphasizing that our exploration will likely always rely on robotic proxies, while our physical presence remains confined to a tiny fraction of the universe. And yet, even within this limitation, humanity can observe, measure, and understand, pushing knowledge far beyond what the body can endure and leaving a record of our existence for the cosmos to receive. When we imagine travelling to the stars, the first instinct is to think faster, to accelerate beyond current speeds. Yet physics imposes strict limits on propulsion. Chemical rockets, even at their maximum efficiency, can barely escape Earth's gravity, achieving velocities insufficient to reach other stars within a human lifetime. Nuclear thermal propulsion offers higher exhaust velocity, reducing travel times to distant planets, but still falls far short for interstellar journeys. Even nuclear electric propulsion, with continuous low-thrust ion drives, can achieve higher speeds over decades, yet the cumulative duration remains impractical for humans. Fusion propulsion, theoretically capable of reaching several % of light speed, would allow a trip to Proxima Centauri in perhaps 85 years, still requiring an entire human lifespan to complete. Antimatter propulsion offers unparalleled energy density, converting mass directly into energy, but production, storage, and containment of sufficient antimatter remain beyond feasible engineering. Each method also compounds challenges. Increased speed demands more shielding, more fuel, more structural mass, and more life support resources, creating a cascade of engineering and biological constraints. Even if we could accelerate to relativistic speeds, interstellar particles, cosmic radiation, and micrometeoroid impacts become lethal hazards. Time dilation offers theoretical relief by slowing subjective experience, yet the energy requirements to accelerate a multi-ton spacecraft to near-light velocity exceed the total energy humanity can currently produce. Every propulsion solution intersects with the realities of mass, energy, and survival, showing that speed alone cannot overcome the biological limits of humans. The fastest machines humanity has built, like Voyager 1 or New Horizons, travel without life support, without vulnerability to radiation, without need for consumables. Humans cannot simply scale these concepts. Every kilogram of additional mass multiplies energy and engineering requirements, revealing that distance is not merely a problem of time, but of survival, energy, and sustainability. Understanding these limitations reframes our expectations. While machines can explore, humans are confined by an interplay of physics and biology, and no amount of desire or courage can bypass the constraints that govern the universe. The boundary set by propulsion demonstrates that interstellar travel for humans is not a linear challenge but an exponential one. where incremental improvements in speed do not translate into proportionate gains in reach, and every leap forward demands disproportionately greater resources. The laws of motion, energy conservation, and mass create a ceiling that is practical, measurable, and ultimately insurmountable for biological explorers. Beyond the protective magnetosphere of Earth, radiation becomes one of the most formidable obstacles to human space travel. In deep space, astronauts are exposed to solar energetic particles from flares and coronal mass ejections, as well as galactic cosmic rays originating from outside the solar system. Galactic cosmic rays are composed of high-energy heavy ions that penetrate shielding, damaging DNA, and increasing lifetime risk of cancer, cardiovascular disease, and neurological impairments. Even thick layers of aluminum, polyethylene, or water provide only partial protection, and poorly designed shielding can exacerbate exposure by producing secondary radiation. During a round-trip mission to Mars, cumulative exposure already exceeds NASA's career limits for astronauts before arriving on the surface, and longer missions to Jupiter, Saturn, or beyond would multiply these risks many-fold. In addition to physical harm, irradiation imposes operational constraints, electronics degrade, instruments fail, and life support systems must compensate for particle-induced malfunctions. For humans, there is no safe level of indefinite exposure. The longer the duration, the greater the damage. Microgravity amplifies the problem by weakening bone and muscle, altering cardiovascular and immune function, and impairing vision. All of these effects combine with radiation to create an environment where survival is uncertain, even before considering isolation or consumables. Robots avoid these constraints entirely. They do not age, do not suffer DNA damage, and do not require continuous physiological support. Probes can traverse the radiation belts of Jupiter, Saturn, and beyond, equipped with shielding just sufficient to protect fragile electronics, and operate for decades. Humans, however, are bounded by biology, making deep space radiation an invisible, omnipresent barrier that defines the limits of human exploration. Even with optimistic assumptions about future shielding technologies, the risk to crew health imposes practical limits on mission duration, distance, and target selection. Radiation is not an incremental hazard. It grows with every mile traveled, making outer planets and interstellar destinations effectively unreachable for human crews. Understanding radiation as a boundary emphasizes that the human frontier is not simply a matter of ambition or technology, but a combination of physics, biology, and survival constraints that converge to create an absolute limit. In space, life support is the silent backbone of any human mission, and it becomes increasingly complex as distance and duration grow. On the International Space Station, astronauts rely on a combination of oxygen generation, water recycling, carbon dioxide scrubbers, and carefully rationed food, all resupplied regularly from Earth. For short-term missions, these systems are sufficient, but a journey to Mars, Jupiter, or beyond multiplies every requirement by months or years. For a 3-year Mars mission, food, water, and oxygen must be stored, recycled, and continuously maintained without error. Any system failure becomes critical because resupply from Earth is impossible. Water recovery systems must reclaim nearly every drop of moisture from waste, including sweat, urine, and exhaled breath. Oxygen must be regenerated from water using electrolysis or carried in pressurized tanks. Carbon dioxide scrubbing systems must remove toxic buildup efficiently, or the crew faces suffocation. Temperature regulation, humidity control, and waste management also become life or death systems, each requiring redundancy and constant monitoring. Every kilogram added to life support increases the total mass of the spacecraft, which in turn multiplies the fuel required for propulsion, the structural demands on the vessel, and the complexity of mission planning. Life support failures are not hypothetical. Even on Earth, closed ecological systems have struggled to maintain stability for more than a few years. Biosphere 2, the most ambitious attempt at a self-contained ecosystem, encountered oxygen depletion, crop failures, and species die-offs within just 2 years. Now, imagine extending that challenge to a multi-year interplanetary mission with humans dependent on these systems for survival. Beyond Mars, the demands intensify dramatically. A mission to Jupiter's orbit lasting 6 years with minimal surface activity requires life support capable of maintaining air, water, and food for years without intervention. Shielding must protect against galactic cosmic rays, and energy must power both life support and propulsion. The closed-loop systems cannot tolerate degradation. Even minor imbalances in gas composition, microbial populations, or water chemistry could threaten the entire crew. Microgravity complicates life support further, as fluids behave unpredictably, affecting waste processing, water recycling, and medical procedures. Additionally, the psychological burden of isolation and confinement interacts with life support. Stress, sleep disruption, and social tension can lead to mistakes in monitoring or maintenance that amplify risks. In interstellar contexts, life support challenges become near impossible. A generation ship, intended to sustain multiple human generations, would need systems functioning flawlessly for centuries. Soil microbiomes, plant growth, atmospheric balance, and waste recycling must remain stable over hundreds of years without external correction, a task far beyond current or foreseeable engineering capabilities. Even if all physical systems are perfectly designed, biological unpredictability, disease, mutation, or ecological drift introduces uncertainty that cannot be fully mitigated. Life support, therefore, is not just a technical requirement. It is the central constraint defining the human reach into space. The limits of oxygen, water, food, waste processing, and energy dictate mission duration, distance, and feasibility. Each step beyond the moon magnifies these challenges exponentially, revealing why the human frontier is bounded not by imagination, but by the practical realities of sustaining life across the void of space. Every mission, every plan, every technological advance must reckon with the inescapable truth that life support is finite, fragile, and utterly essential for survival, and that even small errors in the systems can have catastrophic consequences when humans travel beyond the near-Earth environment. The human body evolved in a gravitational environment, and the absence of gravity in space fundamentally alters physiology in ways that compound over time. In microgravity affect every system: skeletal, muscular, cardiovascular, neurological, and even ocular. Bone density loss occurs at approximately 1 to 2% per month in weight-bearing bones, such as the hip, pelvis, and spine. Exercise countermeasures slow this loss but cannot fully prevent it, and extended missions risk fractures from minor accidents, a situation that becomes life-threatening far from Earth. Muscle atrophy follows a similar trajectory. Skeletal muscles weaken without resistance, and cardiac muscles remodel, losing efficiency and endurance. Vision changes, now classified as spaceflight-associated neuroocular syndrome, can involve flattening of the eyeball, optic nerve swelling, and altered cerebrospinal fluid pressure, compromising the ability to perform critical tasks. The immune system is suppressed in microgravity, reactivating latent viruses and reducing the capacity to respond to infections, while kidney function is impaired, increasing the risk of stones and progressive renal damage. Even the digestive system is affected, with altered fluid distribution and metabolism. These physiological changes are manageable on the International Space Station with 6-month rotations, frequent exercise, and quick return to Earth. However, on missions extending years or decades, especially beyond Mars, the cumulative effects become insurmountable. Continuous exposure to microgravity, combined with radiation and isolation, accelerates degeneration, threatening not just performance, but survival. Countermeasures such as artificial gravity via spacecraft rotation are conceptually feasible but introduce new engineering and mass challenges that may themselves be prohibitive. Nutritional optimization can mitigate some loss, yet cannot eliminate the fundamental physiological adaptations to weightlessness. The interplay between microgravity, radiation, and isolation creates a cascade of compounding effects. Weakened bones release calcium, increasing kidney stone risk. Reduced muscle mass strains the cardiovascular system. Altered circulation affects vision and neural processing. Every factor magnifies the others, producing a cumulative burden that cannot be fully reversed even upon return to Earth. For interstellar missions, the problem scales exponentially. The longer the journey, the greater the degradation, and the more sophisticated the mitigation systems must be, increasing mass, energy, and fuel requirements. Microgravity is therefore not a minor inconvenience. It is a fundamental boundary that constrains human travel. It transforms distance into risk, duration into hazard, and every additional day in space into a measurable erosion of physical capability. Understanding the effects of microgravity is essential for defining the realistic outer limits of human exploration, emphasizing that even if propulsion, energy, and life support could be solved, biology imposes its own strict and inescapable constraints. Beyond the Moon, beyond Mars, beyond the familiar confines of Earth orbit, the human mind faces challenges as severe as those imposed on the body. Isolation, confinement, and delayed communication become defining factors of survival. Unlike machines, humans require social interaction, mental stimulation, and predictable environments to maintain cognitive and emotional stability. Studies of long-duration missions, such as Mars 500, have demonstrated that crews confined for 520 days experience depression, sleep disruption, cognitive decline, and interpersonal conflict, even knowing that help was physically near. Now imagine the reality of interplanetary travel, where the nearest human is millions of miles away, and communication delays stretch from minutes to hours. Every decision must be made autonomously. Every emergency must be solved with limited resources under extreme stress. The uncertainty of survival, combined with monotony, confined space, and relentless responsibility, magnifies psychological strain exponentially over months and years. Anxiety and stress responses increase, leading to impaired judgment, a reduced problem-solving ability, and conflicts that threaten mission cohesion. Mental health cannot be replenished or supported remotely. Therapy and counseling are unavailable, and social support is minimal. Cognitive decline can compromise operational efficiency, affecting everything from navigation to life support maintenance. Sleep disturbances, common in microgravity, compound the problem, reducing attention, reaction time, and mood stability. Over the years, these cumulative psychological effects become as dangerous as physical threats. A single lapse in judgment or interpersonal conflict could have catastrophic consequences in a context where no rescue is possible. Crew selection and training can mitigate some risks, but no preparation fully replicates the realities of isolation in deep space. Even in highly controlled simulations, Human behavior reveals unpredictability under extreme conditions, and the interactions between stress, cognitive load, and environmental hazards remain poorly understood. In interstellar contexts, the duration of isolation extends into decades, creating scenarios that the human mind has never evolved to manage. Generational missions attempt to address longevity, but introduce their own complexities, maintaining societal cohesion, transferring knowledge, preventing cultural drift, and sustaining morale across generations within a closed habitat. Artificial intelligence and automation may assist with monitoring and operational support, yet cannot replicate the social and emotional interactions necessary for psychological well-being. In every scenario beyond Earth, the human mind emerges as both a limit and a vulnerability. Understanding psychological strain is essential for defining where human travel becomes unsustainable. The outer solar system and interstellar space are not only physically hostile, they are environments that impose mental and emotional challenges as severe and unrelenting as radiation or microgravity. The mind, like the body, establishes boundaries that technology alone cannot overcome, making psychological resilience one of the most critical and least controllable factors in deep space exploration. The interplay of isolation, stress, cognitive decline, and operational demands ultimately dictates how far humans can venture, emphasizing that no matter how advanced propulsion or life support becomes, the human frontier is constrained by the delicate architecture of consciousness itself. As humans confront the harsh limits of biology and psychology, robotic spacecraft emerge as indispensable explorers. Unlike humans, machines do not require oxygen, food, water, or social interaction. They are impervious to radiation, microgravity, and the physical degradation that accompanies long-duration missions. Probes like Voyager 1 and 2, New Horizons, Cassini, and Juno have explored every corner of the solar system, operating in environments that would be immediately lethal to humans. Their longevity is measured in decades, their range in billions of miles, their resilience in conditions that no biological organism could endure. By removing the constraints of life support, radiation shielding for biological tissue, and psychological support, robotic missions reduce mass, energy requirements, and complexity exponentially compared to human missions. These machines can travel far beyond Mars, Jupiter, Saturn, Uranus, and Neptune, collecting data, capturing images, and transmitting knowledge back to Earth over decades or even centuries. They can operate autonomously, adjust to unforeseen circumstances, and function in extreme thermal and radiation environments. Laser sails, ion propulsion, and radioisotope thermoelectric generators exemplify how energy-efficient, lightweight, and durable systems can extend our reach without putting lives at risk. Even interstellar distances, where humans are confined by lifespan and sustainability, become approachable for tiny robotic probes traveling at fractions of light speed. Machines can endure timescales longer than civilizations, coasting through interstellar space, while humans remain bound to short biological lifespans. Robotic exploration provides not only data but context, enabling humans to make informed decisions about future missions, identify hazards, and test technology in environments too extreme for biological survival. They extend the domain of human knowledge far beyond the physical reach of our species, effectively becoming proxies that explore, measure, and witness the universe on our behalf. Every insight gained from robotic missions illuminates the limits and possibilities of human travel, offering a roadmap to where humans might go safely and where biology imposes an insurmountable boundary. In this way, humanity's physical reach is complemented by its technological reach. Our bodies may be fragile and time-limited, but our instruments allow us to touch regions of space we will never walk upon. Robotic proxies illustrate that ambition is not constrained by physical presence alone. They demonstrate that human curiosity, ingenuity, and intellect can traverse distances that life itself cannot survive, defining a frontier of knowledge that surpasses the frontier of survival. Every journey into deep space, whether to Mars or beyond the outer planets, is dictated by the unforgiving laws of energy and mass. Propelling a spacecraft requires fuel, and the more massive the vessel, the more fuel is needed, not linearly but exponentially. Chemical rockets can escape Earth's gravity, but adding life support, shielding, and supplies for humans multiplies mass and energy requirements to staggering levels. Nuclear thermal propulsion offers greater efficiency, yet even this cannot bridge the gap to interstellar distances for biological travelers. Fusion propulsion, while theoretically capable of reaching a few % of light speed, remains a technology centuries from practical implementation. Antimatter propulsion offers unparalleled energy density, but is currently limited by production, storage, and containment challenges that are far beyond any feasible engineering plan. Every additional kilogram of mass, food, water, oxygen, shielding, habitat modules, compounds fuel requirements, which in turn require even more structural mass, creating a feedback loop known in aerospace engineering as the tyranny of the rocket equation. Even with breakthroughs, energy remains the ultimate limiting factor, accelerating, decelerating, and sustaining humans over decades of travel demands energy inputs comparable to centuries of civilization-wide production. For missions within the solar system, this limits payload, duration, and feasible destinations. Beyond Mars, every mission becomes a delicate balance between mass, energy, and survival. Relativistic speeds, proposed as a means to overcome vast distances, introduce extreme energy requirements. Accelerating a 1,000-ton vessel to 90% of light speed, for example, would require energy equivalent to the total global consumption for centuries. Deceleration at the destination doubles this requirement, and shielding against interstellar debris adds yet more mass and energy demand. The reality is that energy availability, not human will, sets the boundary for practical exploration. Even if life support, propulsion, and shielding were optimized perfectly, insufficient energy would render interstellar missions impossible. The interplay of mass and fuel creates a ceiling for achievable speed and distance, demonstrating that propulsion is inseparable from physics. Energy constraints highlight that human travel is bounded not by imagination, but by the finite resources and physical laws governing motion in space. This limitation is absolute. No amount of ambition can bypass the fundamental requirement that moving mass through the cosmos demands energy, and for human-scale missions, the energy scales quickly exceed civilization's capabilities. It is here, at the intersection of energy, mass, and survival, that we see the hard limits of human space travel clearly defined. Every increase in distance or duration magnifies energy demands geometrically, creating a practical wall beyond which humans cannot realistically venture. Understanding energy constraints is essential to appreciating why interstellar travel remains a concept for machines, thought experiments, or distant speculation, while humans remain confined to the inner reaches of the solar system. In spaceflight, mass is the silent tyrant, dictating what is possible, what is safe, and what is survivable. Every kilogram carried on board requires additional fuel, more structural support, and greater energy for acceleration and deceleration. When planning missions to Mars, Jupiter, or the outer planets, life support systems, food, water, oxygen, radiation shielding, and habitat modules all contribute to an exponential increase in mass. This creates cascading challenges. More mass requires more fuel, which requires larger rockets and more powerful propulsion, which in turn increases structural demands and further mass. The effects multiply geometrically, not linearly. For example, adding a ton of shielding to protect against galactic cosmic rays may require several additional tons of fuel, which themselves require additional structure and supplies, creating a feedback loop that rapidly becomes unmanageable. This is why robotic probes, which weigh only hundreds of kilograms, can explore regions humans cannot. They avoid the massive life support, consumables, and protective systems for fragile biology. For humans, every kilogram counts. A multi-year mission requires hundreds of tons of supplies. Even minor increases in mass exponentially increase energy and fuel demands, making long-duration missions to distant planets impractical with current technology. In interstellar contexts, this tyranny of mass becomes absolute. A generation ship designed to transport hundreds of people requires thousands of tons of life support, shielding, and consumables, creating energy and propulsion requirements beyond civilization's capacity. The law of mass highlights a fundamental truth. In space, carrying more always costs more than expected, and small additions cascade into massive consequences. Every mission must balance crew size, habitat volume, shielding, and consumables against the fuel and propulsion capabilities available. There is no margin for error. Exceeding mass limits can prevent launch, compromise acceleration, or render life support unsustainable. The tyranny of mass defines the ceiling of achievable human exploration, emphasizing that distance, duration, and survival are inseparable from the weight of what is carried. Understanding this principle is essential to grasp why humans can explore the Moon and possibly Mars, but why voyages to Jupiter, Saturn, or interstellar space are currently beyond our reach. Mass is not merely a technical concern. It is a fundamental boundary imposed by physics, dictating the outer limits of human presence in space. Every additional kilogram of shielding, oxygen, water, or food pushes the edge of what is physically possible, reinforcing that ambition alone cannot overcome the realities of spaceflight. It is the silent constraint that governs the human frontier, defining where survival ends and imagination begins. Beyond Saturn, the outer planets, Uranus, Neptune, and the Kuiper Belt, represent a frontier where human survival is no longer just difficult, it is practically impossible. Distances stretch into billions of miles, transit times extend into decades, and the environmental hazards multiply in severity. Uranus orbits at roughly 1.8 billion miles from the Sun, Neptune at 2.8 billion miles, and any mission there with conventional propulsion would require decades of continuous travel. During this time, crews face continuous microgravity, radiation exposure from galactic cosmic rays and solar energetic particles, and isolation that intensifies psychological strain. Life support must function flawlessly for decades, recycling oxygen, water, and food without external resupply. Any failure, no matter how minor, could prove fatal, as help is years away and communication delays span hours. The Kuiper Belt, beyond Neptune, introduces additional challenges. Weak sunlight renders solar power ineffective, requiring nuclear energy systems that themselves add mass, complexity, and risk. Pre-positioned cargo or habitat modules would need decades-long reliability under extreme cold and radiation. Every kilogram added for shielding, supplies, or structural integrity amplifies fuel requirements, propulsion needs, and mission complexity, reflecting the exponential scaling of deep space logistics. Psychological effects compound these physical hazards. Extended isolation, confinement, monotony, and delayed communication increase the likelihood of cognitive decline, depression, and conflict, with no possibility of intervention. Robotic spacecraft like Voyager and New Horizons navigate these regions successfully, because they are immune to biology. They require no life support, are radiation tolerant, and can operate autonomously for decades. Humans, however, remain vulnerable to every environmental factor, with failure cascading from one system to another. The outer solar system illustrates the intersection of physics, biology, and engineering that defines the true limit of human space travel. Even if propulsion technology were dramatically improved, the cumulative effects of time, radiation, life support constraints, and psychological stress form a boundary that cannot be crossed by biological humans. The region demonstrates that survival is not incremental, it is absolute. Beyond Saturn, the margin for error evaporates, revealing that while humans can explore nearby planets and moons, the outer solar system is fundamentally inhospitable. Distance is not merely a number. It translates into exposure, decay, and risk that humans cannot survive. Every insight gained from robotic missions to these regions informs our understanding of planetary formation, solar system evolution, and potential resources, but simultaneously underscores the constraints that make human travel there improbable. The outer solar system is a vivid reminder that while knowledge and observation can extend indefinitely, physical presence is strictly limited by biology, energy, and time. Human ambition meets a ceiling here, where the environment, distance, and physics combine to set an absolute threshold for survival. See, Einstein's theory of special relativity introduces a fascinating possibility: time dilation. As objects approach the speed of light, time slows relative to observers at rest. In theory, a spacecraft traveling at 90% of light speed would experience time at roughly 44% of the rate experienced on Earth. A journey of 10 years by Earth's clocks would feel like only about 4.5 years to the crew. At 99% of light speed, a voyage covering 4.24 light years, the distance to Proxima Centauri, would subject the crew to a subjective travel time of just 7 months. This effect provides a tantalizing conceptual solution to the problem of human longevity during interstellar travel, suggesting that with sufficient velocity, crews could reach nearby stars within their own lifespans. However, the energy requirements to accelerate a spacecraft, even a fraction of light speed, are astronomical. Propelling a 1,000-ton vessel to 90% of light speed demands energy equivalent to the total consumption of human civilization over centuries. Deceleration at the destination requires an equal input, doubling the energy demand. Moreover, relativistic travel introduces additional hazards. Interstellar space contains sparse hydrogen atoms and dust. At near-light velocities, even microscopic particles strike the spacecraft with devastating force, capable of eroding shielding and endangering crew survival. Radiation exposure is intensified by relativistic effects, and any collision with debris could be catastrophic. While the mathematics of relativity allows a form of temporal shortcut, the physical constraints of energy, shielding, of life support, and mass make its practical implementation for human crews currently impossible. Machines, however, can exploit these principles without concern for life support, enabling probes to explore distant stars over decades or centuries. Relativity highlights a paradox. The universe allows for subjective shortcuts through time, yet the practical realities of physics, energy, and biology conspire to keep humans firmly confined within the solar system. It demonstrates that even with advanced theoretical concepts, ambition cannot overcome the intersection of time, mass, energy, and survival. Relativistic travel illuminates the boundaries of what is mathematically conceivable versus what is physically achievable for biological humans. It is a reminder that while imagination can contemplate the stars, the body and civilization define the limits of what we can actually traverse. Even if propulsion and life support challenges could be solved, interstellar travel presents hazards that are unique and lethal to humans. Space is not empty. It is filled with interstellar gas, cosmic dust, and high-energy particles. At relativistic velocities, even a single hydrogen atom becomes a projectile with destructive energy. Micrometeoroids and dust grains, harmless at low speeds, strike with enough force to penetrate shielding, damage hulls, and endanger crews. Galactic cosmic rays, composed of high-energy heavy ions, bombard every surface, creating secondary radiation within shielding material and compounding exposure. Unlike Earth or near-Earth orbit, there is no planetary magnetosphere to offer protection. A human crew traversing interstellar space would face cumulative radiation doses far beyond career or lifetime safety limits, leading to DNA damage, cancer, cardiovascular risks, and central nervous system impairment. Medical intervention in these conditions is impossible. Every health problem from minor injury to severe disease must be addressed with only the supplies and expertise on board. Micrometeoroid impacts threaten critical systems, including life support, propulsion, and navigation, requiring unprecedented redundancy and resilience in spacecraft design. Artificial shielding to counter these hazards adds enormous mass, which in turn increases propulsion energy requirements and fuel consumption, creating a feedback loop that rapidly escalates beyond feasible limits. Even a small spacecraft traveling at high velocity would need layers of protection equivalent to hundreds of tons, far exceeding the mass of a crewed vessel. The risks are continuous, omnipresent, and unavoidable. Time itself becomes a hazard as cumulative exposure grows. The interstellar medium is a slow, persistent threat, eroding both the physical structure of the spacecraft and the biological integrity of its occupants. Robotic probes avoid these consequences, enduring interstellar space for decades or centuries, equipped with minimal shielding and designed to tolerate extreme particle flux. Humans, however, cannot. The universe's sparse matter becomes deadly when relative velocities increase, meaning that any interstellar journey for biological crews faces continuous threats that accumulate relentlessly over time. These hazards define a boundary of survivability, a limit imposed not by imagination but by the physical properties of space itself. Even with advanced technology, the combination of debris, cosmic rays, and high-energy particles forms a persistent and inescapable barrier. The outer limits of human travel are determined as much by these invisible threats as by distance, life support, or propulsion. Every mile travelled amplifies the danger, and the longer the journey, the more severe the cumulative impact. The interstellar environment is unforgiving, exposing the fundamental vulnerability of human life in ways that no engineering solution has yet mitigated. The reality is clear. Beyond the solar system, survival itself becomes the ultimate constraint, and biological humans confront an environment that is both empty and lethal. A paradox that defines the outer boundary of feasible exploration. One proposed solution to interstellar distances is the concept of generation ships, self-sustaining vessels designed to carry multiple human generations across light years. In theory, a population aboard a closed ecosystem could reproduce, maintain social structures, and arrive at a distant star while the initial crew has passed away. The concept bypasses the lifespan limitations of individual humans, allowing humanity to persist across centuries-long journeys. Yet the engineering and biological challenges are immense. Closed ecological systems must recycle air, water, and food flawlessly over hundreds of years. Soil, plants, microbial communities, and waste processing systems are inherently chaotic. Small imbalances accumulate, threatening the stability of life support, Biosphere 2 demonstrated that even carefully controlled experiments fail within just a few years, with oxygen depletion, crop failures, and ecological collapse. Scaling this to a self-contained ship with hundreds or thousands of humans multiplies complexity exponentially. Social systems must endure without external governance, education must transmit technical knowledge across generations, and conflict must be resolved internally. Psychological stress is compounded by confinement, isolation, and the knowledge that no one aboard will ever see Earth again. Energy requirements for propulsion, habitat maintenance, and shielding against radiation add mass that further complicates design, creating exponential scaling challenges. Even assuming perfect engineering, the risk of systemic failure is high. A single ecological collapse, a technological malfunction, or social breakdown could threaten the entire population. Radiation remains an unresolved problem. Galactic cosmic rays and solar energetic particles degrade both infrastructure and biological tissue over centuries. The sheer scale of time, mass, and complexity creates a boundary where feasibility meets impossibility. Generation ships illustrate that distance in space is not simply a problem of speed. It is a problem of survival across time, biology, and social structure simultaneously. While conceptually intriguing, generation ships remain speculative, highlighting the extraordinary challenges of sustaining human life over interstellar scales. They underscore the harsh reality that even with multi-generational planning, the human body and human society are fundamentally limited by the environments of space. The concept emphasizes that interstellar travel for humans is less a question of ambition or ingenuity, and more a question of biology, engineering, and the passage of time, marking one of the most extreme boundaries of human exploration. Suspended animation, often called cryo-sleep, is frequently proposed as a solution to the immense durations of interstellar travel. The idea is elegant. Place the crew in a state of biological suspension for decades or centuries, allowing them to awaken at the destination with minimal physiological aging and without the continuous need for food, water, or psychological support. In principle, cryosleep addresses the most limiting factors of deep space travel, including human lifespan, microgravity effects, and prolonged isolation. However, current science does not allow whole-body cryopreservation of humans. While individual cells and small tissue samples can be frozen and revived, and organ preservation remains under active research, no method exists to maintain the integrity of all tissues in a living human over extended periods. Ice crystal formation destroys cellular membranes, metabolic processes cease, and even the most advanced cryoprotectants cannot yet prevent systemic damage at the scale required for a full human body. Reversal of the suspended state without injury has never been demonstrated. Beyond the biological challenges, the engineering requirements for a generational cryosleep vessel are staggering. Systems must monitor and maintain metabolic suspension, prevent ice damage, circulate cryoprotectants, and shield the crew from radiation for decades. Power, thermal regulation, and redundant life support must operate flawlessly over extended periods without repair. Any failure would be catastrophic, potentially compromising all occupants. Cryosleep also eliminates psychological challenges, but it cannot mitigate structural failures, collisions with interstellar particles, or cumulative radiation effects. Even if perfected, suspended animation would only shift the problem from biological endurance to engineering reliability and energy. Moreover, energy requirements to maintain cryosleep, along with shielding and spacecraft systems, remain enormous, compounding the tyranny of mass and fuel already present in interstellar mission planning. Cryosleep, while alluring, is speculative and represents a technological frontier as distant as the stars themselves. It highlights the interplay between human biology and space engineering. Even with theoretical solutions, reality imposes constraints that cannot be ignored. For now, cryosleep remains a concept to inspire imagination and research, rather than a practical method for extending human reach. Its study emphasizes how extreme the barriers to interstellar travel truly are, illustrating that while dreams of suspended crews are compelling, the universe maintains limits that are both physical and biological, defining the boundary of what humans could ever endure. Einstein's theory of special relativity offers a unique perspective on interstellar journeys, suggesting that time itself can provide a form of relief for travelers moving at extreme velocities. As a spacecraft approaches the speed of light, time slows relative to observers on Earth, yet allowing a crew to experience a shorter subjective duration for an otherwise decades-long journey. For instance, a vessel travelling at 90% of light speed would perceive 4.5 years of travel for a trip that lasts 10 years according to Earth clocks. At 99% of light speed, a journey covering 4.24 light years, the distance to Proxima Centauri, would subject the crew to roughly 7 months of subjective time. In theory, this offers a solution to the challenge of human lifespan during interstellar travel, allowing biological crews to survive journeys that would otherwise outlast their lifetime. However, implementing relativistic travel for humans is constrained by extreme energy requirements. Accelerating even a modestly sized spacecraft to such velocities demands energy equivalent to centuries of total human consumption. The deceleration at the destination doubles the energy requirement. An additional mass from shielding, life support, and habitation modules further compounds fuel needs. Interstellar space is not empty. Even at high velocities, collisions with sparse hydrogen atoms, dust, or cosmic rays produce devastating impacts, capable of penetrating shielding and endangering the crew. Relativistic velocities also intensify radiation exposure due to Doppler shifts and particle interactions. While the mathematics of time dilation is real, experimentally confirmed, and provides a theoretical shortcut, the physical realities of energy, shielding, debris, and life support remain insurmountable. Machines, unburdened by life support or biological vulnerability, could benefit from relativistic travel. Exploring nearby stars over decades or centuries, but humans cannot currently exploit this effect safely. Relativity highlights the difference between mathematical possibility and practical feasibility, illustrating that even the most elegant physical laws cannot circumvent biological and engineering limitations. It reinforces the boundary where ambition meets physics, and where the limits of human survival define the ultimate extent of interstellar reach. Time itself becomes a concept that is malleable only in theory. In practice, the universe imposes constraints that remain absolute, reaffirming that the furthest humans could ever travel is determined as much by biology and energy as by speed and distance. Even with the promise of time dilation, the energy requirements for relativistic travel remain staggering. Accelerating a spacecraft to 90% of the speed of light is not a linear challenge, it is an exponential one. The kinetic energy needed increases with the mass of the vessel and the square of the velocity, meaning that small increases in speed require disproportionately massive increases in energy. A 1,000-ton spacecraft accelerated to 90% of light speed would demand energy equivalent to centuries of total global energy production. Deceleration at the destination requires an equal expenditure, and any shielding or life support mass further multiplies energy needs. Beyond the fuel and propulsion concerns, the effects of collisions with interstellar particles intensify at relativistic velocities. Even sub-milligram dust grains strike with energies equivalent to explosives, threatening hull integrity and crew safety. Our radiation effects are magnified, as high-energy particles and photons interact with shielding to produce secondary radiation that can penetrate deeply into the spacecraft. Life support systems must function flawlessly under these extreme conditions for the duration of the journey, and redundancy becomes essential, but adds further mass and energy demand. Even theoretically, relativistic travel exposes the crew to risks that scale with distance, time, and velocity, creating a compounded set of constraints. The laws of physics ensure that energy is the limiting factor. No matter how efficient propulsion technology becomes, accelerating, decelerating, and maintaining life for a multi-ton human-rated vessel at near-light speeds exceeds any energy budget human civilization could reasonably produce. In contrast, robotic probes, which do not require life support or shielding for biological organisms, can traverse interstellar space over decades or centuries with energy requirements orders of magnitude lower than a crewed vessel. Relativistic travel demonstrates a fundamental truth. Time dilation may shorten subjective experience, but it does not circumvent the constraints imposed by energy, mass, and survival. The furthest humans could ever travel is thus limited not only by distance and lifespan, but by the inexorable arithmetic of physics that governs motion and energy in space. Even with hypothetical propulsion breakthroughs, the combination of mass, shielding, life support, and acceleration makes interstellar human travel effectively impossible. Relativistic travel highlights the delicate balance between ambition and reality, emphasizing that the universe imposes boundaries that no ingenuity alone can erase. Every increase in velocity produces a cascade of engineering and biological challenges, reinforcing the principle that survival, energy, and mass are intertwined limits that define the outermost boundary of human space travel. The cosmos permits observation, measurement, and exploration through machines, but the human body remains bound by physics, a reminder of both our fragility and our ingenuity in seeking to understand what lies beyond. Beyond the solar system, interstellar space is far from empty. It contains diffuse hydrogen gas, microscopic dust particles, and high-energy cosmic rays. At sublight velocities, these components pose minimal threat, but at relativistic speeds, even a single hydrogen atom or micrometeoroid becomes a devastating projectile. A collision with an atom or dust grain at near-light velocity can release energy comparable to the detonation of tons of explosives, capable of penetrating hulls and compromising life support systems. Galactic cosmic rays, composed of high-energy heavy ions, further complicate the environment by generating secondary radiation within shielding materials, increasing cumulative exposure for any biological occupant. Unlike Earth orbits, there is no protective magnetosphere. Human crews are fully exposed to the unfiltered hazards of interstellar space. Radiation, particle collisions, and micrometeoroids act continuously, compounding over months, years, or decades of travel. Even thick shielding cannot entirely mitigate these effects without adding prohibitive mass, which in turn increases propulsion energy requirements and complicates engineering. Robotic probes avoid these limitations. They do not suffer biological damage, can tolerate higher levels of radiation, and can survive minor impacts without catastrophic consequences. For humans, the environment imposes absolute limits. The cumulative effect of interstellar debris and cosmic radiation establishes a boundary that cannot be circumvented by better training, courage, or ingenuity. Every mile travelled increases risk exponentially, making long-distance travel far more dangerous than distance alone suggests. Human survival becomes a function not just of life support and propulsion, but of the ability to withstand hazards that cannot be fully predicted or controlled. The interstellar medium, though sparse, transforms into a persistent and deadly challenge at high velocities, illustrating the gap between what machines can endure and what humans can survive. Even if propulsion and life support could be perfected, the universe itself imposes constraints that biology cannot overcome. This invisible barrier defines one of the outermost limits of human space travel, where the survival of a crew is contingent upon factors beyond engineering or planning. It underscores that interstellar distances are not only measured in light years, but in cumulative risk, reinforcing the profound difference between observation, exploration via proxies, and physical human presence in the cosmos. Even if all engineering challenges were solved, human biology imposes non-negotiable limits on space travel. Life evolved under Earth's gravity, magnetosphere, and atmospheric conditions, and deviations from these parameters create cascading physiological problems. Microgravity causes rapid bone density loss, with 1 to 2% per month in weight-bearing bones, increasing fracture risk. Skeletal muscles atrophy despite exercise, cardiac muscles remodel, and ocular structures can deform, producing vision impairment. The immune system weakens, latent viruses reactivate, and wound healing slows. Kidneys and other organs are stressed, with calcium released from demineralized bones, increasing the risk of kidney stones. Extended exposure to galactic cosmic rays compounds these effects, damaging DNA, inducing cancer, cardiovascular disease, and central nervous system decline. In combination with long isolation periods, sleep disruption, and limited mobility, these physiological effects amplify the likelihood of catastrophic failure in long-duration missions. Even with artificial gravity, advanced shielding, and optimized nutrition, these effects cannot be entirely mitigated. A mission beyond Mars or to the outer planets would require the crew to endure years of progressive physical deterioration with limited capacity for recovery. Generational missions or cryosleep may offer theoretical workarounds, but these solutions are speculative, untested, and themselves introduce new layers of risk. Life's fragility becomes a fundamental constraint. Regardless of propulsion, energy, or shielding, human survival cannot be guaranteed over decades-long interstellar journeys. This principle highlights why robotic probes have been humanity's primary means of exploring distant planets and interstellar space. Machines are not vulnerable to bone loss, muscle atrophy, immune suppression, or radiation-induced DNA damage. They can operate autonomously for decades or centuries, transmitting data without physical degradation. Biological limits define the human frontier in space. A combination of lifespan, physiological stress, and cumulative radiation exposure sets a boundary that no current or foreseeable technology can overcome. Even under the most optimistic projections of future propulsion and life support, these biological constraints are absolute. They dictate mission duration, distance, and target selection, ensuring that humans remain confined to the inner solar system while machines explore the outer planets and interstellar space. The fragility of life underscores the stark reality. Human ambition meets physics and biology, and the limits imposed by life itself are as formidable as any environmental or engineering challenge. It is these constraints that define the outermost boundary of feasible human space travel, where distance is not simply measured in miles or light years, but in the endurance and resilience of the human body. Generation ships have long been proposed as a solution to interstellar distances that exceed human lifespans. The concept involves sending a self-sustaining population across light years, with each generation maintaining the ship until the destination is reached. While theoretically solving the problem of lifespan, is that the practical challenges are extraordinary. Closed ecological systems must recycle air, water, and nutrients flawlessly for centuries, Without external resupply or intervention, soil, plant, and microbial communities are inherently unstable over such long periods. Small imbalances can cascade into life-threatening failures. Social systems must persist without collapse. Education must transfer technical knowledge across generations, and governance must function autonomously. Psychological stress is magnified when individuals are born, live and die aboard a confined ship, knowing they will never see Earth or the destination. Propulsion requirements remain immense, and energy demands for shielding, habitat life support, and course corrections increase with mass and distance. Radiation is an unavoidable hazard. Over centuries, galactic cosmic rays and solar energetic particles would accumulate, affecting both human occupants and structural integrity. Even assuming perfect engineering, the risk of failure is high, and redundancy cannot guarantee survival. Any collapse of the ecological, technical, or social system would threaten the entire population. Generation ships illustrate the scale of interstellar challenges. Human biology, engineering, and societal stability must all function in concert over centuries. These constraints reveal why even a well-designed ship may be incapable of safely delivering humans to another star. Robotic exploration, by contrast, avoids these limitations entirely, requiring orders of magnitude less mass, energy, and system complexity. The concept of generation ships highlights a critical truth. While imagination allows us to envision multi-generational voyages, reality imposes overlapping constraints of life support, radiation, energy, and sociology that remain unsolved. Even under optimistic assumptions, these vessels lie at the edge of theoretical possibility, emphasizing that the practical boundary of human space travel is set not just by distance, but by the endurance of life, society, and technology across centuries. The idea reinforces the central lesson of interstellar exploration. Human presence is fundamentally limited, and survival depends on multiple factors that cannot be optimized independently. Suspended animation, or cryo-sleep, presents one of the most alluring theoretical solutions to the problem of interstellar travel. The idea is to place humans in a biologically inert state, halting aging, metabolism, and resource consumption for decades or even centuries, allowing a crew to awaken at the destination without having physically experienced the journey. In theory, this could overcome human lifespan limitations and the cumulative effects of microgravity, radiation, and psychological strain. However, current science has yet to demonstrate the feasibility of full-body cryopreservation. While individual cells and small tissue samples can survive freezing and reanimation, entire organs present challenges due to ice crystal formation, cellular rupture, and metabolic disruption. Cryoprotectants help mitigate damage, but even the most advanced formulations cannot fully prevent systemic failure across a whole human. Near reversal from suspended states has not been achieved for complex organisms, and scaling the process for multi-person spacecraft introduces exponential complexity. Beyond biological barriers, engineering requirements for cryosleep are immense. Systems must maintain precise temperatures, monitor metabolic activity, circulate cryoprotectants, and shield occupants from cosmic radiation for decades. Power, structural integrity, and redundant life support must function flawlessly without human intervention. Even minor malfunctions could jeopardize the entire crew. Cryosleep, therefore, remains speculative, a concept more suited to thought experiments or science fiction than practical implementation. Yet it highlights a critical point. The fundamental limitations of human biology and engineering intersect to define the outer boundary of feasible travel. Even if propulsion, shielding, and life support were perfected, the inability to reliably suspend and preserve humans over long durations imposes a hard limit. This technology, if ever realized, could redefine the possible, but for now it emphasizes the gap between human ambition and biological reality. Suspended animation also demonstrates that distance in space is not simply a matter of miles or time, but of sustaining life across extreme environments without degradation. It underlines why robotic probes have been humanity's primary means of exploring distant systems. Machines require no metabolism, age, or psychological support, and they endure hazards that humans cannot. Cryosleep embodies the tension between imagination and physics, illustrating that while concepts may exist, survival defines the boundary of reality. The idea encourages research, innovation, and contemplation, yet reinforces that the furthest humans could ever travel remains limited by the combined constraints of biology, engineering, and physics. Even the most optimistic theoretical solutions highlight that human exploration is confined to a small fraction of the cosmos, where survival is possible and ambition must be tempered by reality. Time dilation, a direct consequence of Einstein's special relativity, offers a theoretical method for humans to traverse interstellar distances within a subjective lifetime. As velocity approaches the speed of light, onboard clocks slow relative to observers on Earth. A spacecraft travelling at 90% of light speed would experience less than half the passage of time, making a decades-long journey feel like only a few years to the crew. At 99% of light speed, a voyage to Proxima Centauri, 4.24 light-years away, would take roughly 7 months of subjective time, even though Earth observers measure the journey in decades. In principle, this offers a solution to the lifespan limitation for biological travellers. However, the practical barriers are enormous. Accelerating even a modestly sized multi-ton spacecraft to such velocities requires energy equivalent to centuries of total human consumption. Deceleration at the destination doubles this requirement. Interstellar space itself is hazardous at these speeds. Even microscopic hydrogen atoms, dust, or cosmic rays impact with devastating energy. Shielding against these impacts requires massive material, which in turn increases propulsion energy requirements and engineering complexity. Life support, habitat structure, and redundancy must remain flawless for the duration of the journey, magnifying mass and fuel demands. Radiation exposure is intensified, and collisions with interstellar particles could be catastrophic. While relativity allows a temporal shortcut, it does not solve fundamental engineering or biological constraints. Machines can exploit time dilation without concern for life support, mass, or radiation vulnerability, but humans remain vulnerable. The practical application of relativistic travel for humans is far beyond current or foreseeable technology, limited by energy, mass, shielding, and survivability. Time dilation illustrates the distinction between mathematical possibility and achievable human exploration. Even if physics permits shorter subjective travel, biology and engineering impose absolute limits. It emphasizes that human ambition, while vast, is constrained by laws of nature that cannot be overridden. The furthest humans could ever travel remains defined not just by distance, but by the intersection of time, survival, energy, and physical law. Relativistic travel highlights that even elegant theoretical solutions encounter insurmountable barriers when biology is involved, reinforcing the boundary where human presence ends and imagination begins. As spacecraft approach relativistic speeds, new hazards emerge that are absent at lower velocities. Interstellar particles, hydrogen atoms, dust grains, and cosmic rays impact the spacecraft with immense kinetic energy. Even sub-milligram particles strike with explosive force, capable of penetrating hulls, damaging life support and threatening crew survival. At 90% of light speed, these impacts are no longer minor, they're continuous high-energy bombardments. Galactic cosmic rays compound the danger, producing secondary radiation when they interact with shielding materials, further increasing exposure to the crew. Life support systems must withstand these conditions while maintaining stable oxygen, water, temperature, and waste processing for the duration of the journey. Even minor malfunctions, when multiplied across years or decades, could become catastrophic. Shielding must be thick enough to absorb energy from relativistic impacts. Yet every additional kilogram adds to the spacecraft's mass, increasing propulsion requirements exponentially due to the tyranny of the rocket equation. Energy demands skyrocket, and the margin for error diminishes with every kilometre travelled. Robotic probes, designed without life support or biological vulnerability, survive these conditions because they do not need protection from radiation, microgravity, or psychological stress. For humans, however, these relativistic hazards define a boundary that cannot be crossed with current or foreseeable technology. The universe itself enforces limits. No matter how advanced propulsion or shielding becomes, the continuous barrage of high-energy particles and radiation remains lethal. Interstellar travel transforms from a question of ambition to a problem of physics and biology, where the environment itself becomes an active barrier. Even theoretical solutions, including fusion propulsion or cryosleep, cannot eliminate the risk. Each increase in velocity intensifies exposure, illustrating that distance is inseparable from hazard. Relativistic travel, while offering the allure of time dilation, simultaneously magnifies physical danger, reinforcing that speed alone cannot overcome the fundamental limitations of human survival. The harsh reality is that interstellar space, though conceptually traversable, is biologically insurmountable. Machines can explore it, endure it, and return data, but humans remain constrained by cumulative radiation, impacts, and physiological vulnerability. These hazards define one of the outermost practical boundaries of human presence, where the cosmos itself enforces a limit on exploration, emphasizing that survival, not curiosity, determines the feasible reach of humanity. Throughout the solar system and beyond, a stark distinction emerges between what machines can achieve and what humans can survive. Robotic probes have explored every planet, flown past Pluto, orbited Saturn, and crossed into interstellar space. They operate in environments lethal to biological life, enduring radiation, microgravity, extreme temperatures, and isolation for decades or centuries. Their design is optimized for survival in conditions where humans cannot exist. Humans, by contrast, require air, water, food, and protection from radiation. They age, weaken, and are susceptible to cognitive and physiological degradation over time. Every kilogram of consumables, shielding, and habitat required for humans multiplies mass, energy, and propulsion requirements exponentially, creating a feedback loop that rapidly exceeds practical engineering capabilities. Even the most advanced propulsion systems cannot overcome these constraints without encountering insurmountable limits of mass, energy, and life support. This gap explains why humanity has explored the entire solar system robotically, while human missions have remained confined to the Moon and low Earth orbit. It is not a question of courage, motivation, or intelligence, but of biology and physics. Human survival defines the boundary of feasible exploration, while machines can push far beyond it, limited only by engineering, power, and patience. Interstellar distances, relativistic hazards, and cumulative radiation create an environment where human life is unsustainable, whereas small, resilient, autonomous probes thrive. Understanding this distinction is critical. Our imagination allows us to conceive of distant worlds, yet our bodies impose hard limits. While humans can dream of standing on Europa's ice or flying past Proxima Centauri, the reality is that machines will continue to carry our curiosity forward, mapping, measuring, and transmitting knowledge where human presence is impossible. The gap between machines and humans highlights that exploration is not solely a question of will, but of survival. It underscores the boundary where biology ends and observation begins, and it defines the furthest humans could ever travel within the constraints of physics, energy, and life itself. Robots extend our reach, but the physical presence of humans remains limited, emphasizing the profound interplay between ambition, survival, and the universe's indifferent scale. Even if biology, propulsion, and energy could theoretically support long-distance space travel, human civilization itself imposes limits on what can be sustained. Multi-year or multi-decade missions require continuous funding, political stability, and social organization capable of maintaining the mission's objectives without interruption. Historical examples such as the Apollo program demonstrate that large-scale space projects demand concentrated effort, immense resources, and unwavering national or international commitment. The Apollo program lasted just 12 years, and the International Space Station has required 25 years of sustained cooperation among multiple nations to operate continuously. Extrapolating to interstellar travel, a mission to a nearby star might require centuries of uninterrupted focus, investment, and coordination. No human institution has ever maintained a single engineering endeavour for such durations. Political upheaval, economic crises, and societal change all threaten long-term projects. Even if propulsion, shielding, and life support were perfected, maintaining human civilization capable of sustaining interstellar missions represents a boundary rarely acknowledged. Generation ships or multi-century missions introduce additional social complexity. Governance, education, conflict resolution, and cultural continuity must persist across generations. Any breakdown in these systems could jeopardize survival. This highlights that human exploration is not limited solely by biology or physics, but also by societal endurance. Civilization's fragility imposes practical limits on interstellar ambitions. Without stable institutions, funding, and coordination, missions cannot proceed, regardless of technological feasibility. The human frontier is therefore defined not only by the constraints of life, energy, and propulsion, but also by the capacity of societies to commit resources and maintain continuity over unprecedented timescales. Understanding these limitations reframes expectations for deep space exploration. Even if a crew could survive the journey, the social and economic infrastructure required to sustain it may not endure. This convergence of biological, technological, and civilizational constraints establishes an absolute boundary for human space travel. Knowledge can extend indefinitely through robotic probes, telescopes, and communication, but physical human presence is confined by the limits of civilization itself. Recognizing this reality provides a holistic understanding of why the furthest humans could ever travel is far less than imagination or science fiction suggests, emphasizing that ambition alone cannot overcome the intersection of biology, physics, energy, and society. When all constraints, biology, energy, propulsion, radiation, mass, and civilization, are considered together, the furthest humans could ever travel amounts to a fraction of a light year. Even with optimistic assumptions about fusion propulsion, closed-loop life support, radiation shielding, and psychological preparation, the maximum feasible distance extends only into the inner regions of the Oort Cloud, roughly 16,000 astronomical units, or about 1/4 of a light year. This distance places a crew farther than any human has ever been by nearly 100-fold compared to Voyager 1, yet it is infinitesimal compared to interstellar scales. For perspective, the nearest star, Proxima Centauri, lies 4.24 light-years away, more than 16 times farther than the maximum plausible human journey. Achieving even this distance would require a spacecraft capable of sustaining life for years, possibly decades, with robust energy, shielding, and life support systems. Communication with Earth would become delayed by months or years, and rescue or resupply would be impossible. The journey would traverse dark, cold regions of space, isolated from any planetary body or solar system infrastructure. Even if propulsion and life support function flawlessly, the biological toll, exposure to cosmic radiation, and psychological strain create absolute limits. This highlights a profound reality. Human exploration is fundamentally constrained by the intersection of physics, biology, and engineering. While machines can extend far beyond these boundaries, humans are restricted to a relatively tiny volume of space surrounding the Sun. The vast majority of the galaxy and the universe itself remains inaccessible to biological travelers. Yet this limit does not diminish the achievements of human exploration. We have already set foot on the Moon, operated in orbit, and extended our understanding of the solar system through robotic probes. The maximum human reach, while limited in scale, represents an extraordinary triumph of ingenuity, resilience, and ambition. It also reframes our perspective. While imagination and curiosity may reach distant stars, the physical presence of humans remains confined to a sphere of influence determined by survival, energy, and time. Understanding the scale of this boundary fosters appreciation for the achievements we have made, the challenges we face, and the profound contrast between what we can know and what we can physically experience in the cosmos. Even though humans cannot physically traverse interstellar distances, our observational reach far exceeds our biological limitations. Telescopes, satellites, and robotic probes allow us to detect and study stars, galaxies, and exoplanets billions of light-years away, revealing a universe unimaginably larger than what we could ever visit. Through electromagnetic signals, visible light, radio waves, X-rays, and more, we gather information from regions that no human could survive reaching. Our understanding of cosmic structures, planetary systems, and galactic evolution is built on the capacity to observe, measure, and analyze without physically being present. Even as Artemis 2 astronauts broke records for human travel, Voyager 1 continues silently, carrying data from the fringes of the solar system, while humanity interprets its signals to understand interstellar space. Light from distant galaxies takes billions of years to reach us, meaning that when we observe these regions, we are seeing the universe as it was long before humans existed. This capability highlights a crucial distinction. While our bodies are bounded by time, mass, and biology, our knowledge is not. We can reach the stars conceptually and scientifically, even if we cannot touch them physically. Electromagnetic signals from Earth's own technology, radar, television, and radio, have already travelled tens of light-years, forming an expanding sphere that could be detected by other civilizations. In this sense, human influence extends farther than human presence. While life is confined, intellect and observation travel at light speed. This paradox underscores the unique position of our species, constrained by survival, yet empowered by knowledge. Machines and instruments act as extensions of our senses, allowing us to interact with regions of space that our bodies could never endure. The gap between physical presence and observation demonstrates that exploration is not solely defined by travel, but by the ability to perceive, analyze, and understand. Even if the furthest humans could only reach a fraction of a light year, our instruments extend our reach across the cosmos, capturing phenomena that occur millions or billions of light years away. This duality, limited presence, unlimited observation, defines the modern frontier of human space exploration and emphasizes that while humans may never walk among the stars, we can still know them. The universe permits comprehension far beyond survival, allowing humans to push the boundaries of understanding even as biology enforces absolute physical limits. Observing beyond, therefore, becomes both a privilege and a responsibility, and demonstrating that the reach of human curiosity surpasses the reach of human feet. While humans are biologically limited, our signals can traverse interstellar distances, effectively extending our presence. Since the early 20th century, electromagnetic waves from Earth, radio, television, and radar transmissions have propagated outward at the speed of light, creating an expanding sphere currently reaching roughly 80 to 90 light-years in radius. Within this region, any sufficiently advanced civilization could, in principle, detect signs of our existence long before a human could physically arrive. These signals carry no mass, require no life support, and are unaffected by cosmic hazards, allowing information to travel farther and faster than any crewed mission could achieve. In effect, where our knowledge and influence extend beyond the constraints of biology and physics, the gap between observing and physically reaching is immense. A signal can cross dozens of light years in decades, while a human travelling at near optimal propulsion would require millennia to traverse the same distance. Communication, data transmission, and electromagnetic observation allow humanity to interact with the cosmos conceptually, mapping planets, analysing stellar composition, and understanding galactic evolution without leaving the solar system. Even interstellar probes like hypothetical gram-scale laser sail missions could reach neighbouring stars in a few decades, transmitting data back across the void while humans remain safely on Earth. These methods highlight the asymmetry between physical exploration and informational exploration. Humans are constrained by lifespan, mass, energy, and radiation, whereas data, signals, and robotic systems extend our reach indefinitely. This principle reframes human space exploration. We may never walk on Europa or Proxima Centauri, yet through observation and communication, we exert influence and gain understanding far beyond the limits of biological presence. The universe responds to inquiry, and our signals form a legacy that continues to propagate, representing humanity across distances that our bodies could never survive. In this sense, while the furthest humans could ever travel is a small fraction of a light year, our presence is effectively multiplied through information, instruments, and electromagnetic communication, ensuring that knowledge and influence outpace physical traversal. Robotic exploration has become humanity's primary tool for reaching the farthest regions of space, precisely because humans cannot survive the extreme conditions. Probes such as Voyager 1 and 2, New Horizons, Cassini, and Juno operate in environments that would be lethal to humans, enduring cosmic radiation, microgravity, and decades of isolation without life support. These machines are engineered for resilience, able to withstand harsh temperatures, high energy particles, and collisions with micrometeoroids, all while continuously transmitting data back to Earth. Unlike human crews, robots do not require oxygen, food, water, or psychological support, drastically reducing mass and energy requirements. The robotic spacecraft demonstrate that exploration does not require presence. Intelligence, instruments, and communication extend humanity's reach. They provide data that informs future missions, identifies hazards, and maps distant worlds, effectively serving as proxies for humans. Even theoretical interstellar missions such as laser-propelled gram-scale probes rely on the same principle. Information can travel where life cannot. The contrast between human vulnerability and robotic endurance underscores why physical presence in space is severely limited. While humans may dream of walking on Europa or visiting Proxima Centauri, these ambitions remain constrained by biology and physics. Machines, by contrast, can operate for centuries, pushing the boundaries of knowledge across immense distances. Robotic exploration thus extends humanity's influence far beyond what is physically survivable, allowing us to understand the universe in unprecedented detail. Every instrument and signal represents a bridge between human curiosity and the inaccessible reaches of space, highlighting that while our bodies are confined, our intellect and technology are not. This approach demonstrates that the furthest humans could ever travel is defined not only by survival, but by our capacity to build proxies capable of transcending physical limitations. The achievements of robotic exploration emphasize that knowledge, rather than physical presence, is the ultimate frontier, enabling humanity to touch regions of space that our bodies cannot endure. It also reframes our ambitions. Exploration is not solely measured by distance traveled, but by the insights gained, the data collected, and the understanding of cosmic processes made possible through machines designed to survive where humans cannot. The furthest humans could ever travel is not a specific planet, moon, or star. It is defined by the intersection of survival, energy, time, and propulsion. Even under the most optimistic assumptions, fusion propulsion at 5% of light speed, closed-loop life support, radiation shielding, and psychological preparedness, the practical limit extends only into the inner regions of the Oort Cloud, roughly 16,000 astronomical units, or 1/4 of a light year. This distance, while far beyond any human has ever physically reached, is minuscule compared to interstellar scales. A journey to this region would require decades, with continuous life support, shielding, and energy, while communication with Earth would become impractically delayed. Beyond this threshold, biological limits, aging, radiation exposure, microgravity effects, combined with engineering and energy constraints, prevent survival. Civilization itself imposes additional limitations. Sustaining projects over decades or centuries is historically unprecedented. The outer boundary of human presence is therefore a practical, enforceable limit, not simply a theoretical one. While knowledge and observation extend far beyond this boundary, the physical presence of humans is constrained to a small sphere surrounding the Sun. Robotic probes extend our influence, travel farther, and endure conditions that humans cannot, but the human body cannot survive the cumulative stresses of interstellar space. Even with breakthroughs in propulsion, life support, or cryosleep, the convergence of these constraints creates an absolute threshold. This defines the ultimate human frontier, a region where ambition, ingenuity, and determination encounter the hard limits of biology, physics, and civilization. Recognizing this boundary is not a limitation of imagination, but a reflection of reality, emphasizing both the fragility and resilience of human life. Within this sphere, humans can explore, learn, and expand knowledge. Beyond it, machines and signals extend our reach. The furthest human frontier illustrates the distinction between potential presence and achievable survival, framing the cosmic scale in which our species exists and highlighting the extraordinary accomplishments already achieved within these bounds. Understanding this boundary also provides perspective. The universe is vast, Our presence is small, yet our capacity to observe, measure, and comprehend far exceeds what our bodies could traverse. Standing on Earth, looking up at the stars, it is easy to feel the vastness of the universe and the smallness of our presence. Even the furthest humans could ever travel, a fraction of a light year into the Oort Cloud, represents an almost infinitesimal distance on the cosmic scale. The Milky Way spans roughly 100,000 light-years, containing hundreds of billions of stars, and the observable universe stretches over 93 billion light-years. Within this incomprehensible expanse, humans are confined to a tiny sphere surrounding the Sun, limited by biology, energy, and survival. Yet despite these constraints, our species has achieved extraordinary feats. We have walked on the Moon, or sent robotic emissaries to every planet in the solar system, and detected light from galaxies billions of light-years away. The contrast between our physical reach and our observational capacity highlights a unique aspect of humanity. We can perceive and understand regions of the cosmos that we could never physically visit. Robotic probes extend our presence, signals travel at the speed of light, and instruments allow us to map planets, stars, and galaxies far beyond our physical limitations. This cosmic perspective emphasizes both humility and awe. While our bodies are confined to a small portion of space, our knowledge and influence extend far beyond, allowing us to engage with the universe in ways that no other species can. The vast distances, extreme conditions, and cumulative hazards define boundaries, but within these limits, grey human curiosity, ingenuity, and observation shine. Recognizing our place in the cosmos provides context for the limits of human travel. It is not failure that confines us, but the interplay of physics, biology, and engineering. We're capable of extraordinary accomplishments within these bounds, achieving knowledge, exploration, and presence in ways that transcend our physical fragility. Understanding the cosmic scale and our relative position within it shapes how we approach space exploration, highlighting that even constrained presence can coexist with limitless understanding. Humanity's achievements, though minute in spatial terms, are monumental in perspective, demonstrating that exploration is not solely measured by distance travelled, but by knowledge gained and the expansion of awareness across space and time. The cosmos invites observation, and even within the limits of survival, humans continue to reach outward through curiosity, intelligence, and technology, bridging the gap between presence and perception. After examining physics, biology, propulsion, energy, radiation, life support, and civilization, the conclusion is clear. The furthest humans could ever travel lies within the inner reaches of the Oort Cloud, roughly 16,000 astronomical units, or a quarter of a light year. This boundary is not arbitrary. It is dictated by the intersection of human endurance, engineering capability, and physical laws. Beyond this threshold, microgravity, radiation, energy requirements, and isolation create conditions that no human body could survive, even with theoretical propulsion or cryo-sleep. Civilization's capacity to maintain long-duration projects, of the tyranny of mass and fuel, and the exponential scaling of life support and shielding all reinforce this boundary. While robotic probes can traverse the outer solar system, the Kuiper belt, and interstellar space, humans are confined to a tiny sphere surrounding the Sun. Within this limit, remarkable achievements are possible. Moon landings, Mars missions, and deep space observations expand our knowledge and inspire future exploration. Beyond it, ambition encounters immutable laws. Speed, energy, survival, and time converge to create an absolute frontier. Recognizing this threshold is not a limitation of imagination, but an acknowledgement of reality. one that frames human accomplishments in perspective. We can observe, measure, and understand regions far beyond our physical reach, sending signals, data, and robotic proxies to explore where life cannot. The gap between what we can touch and what we can know defines the paradox of human existence in a vast universe. Our presence is small, yet our understanding is immense. The furthest humans could ever travel is both humbling and awe-inspiring, a reminder of our fragility and ingenuity. It is a reckoning that honours what we have achieved, illuminates the scale of the cosmos, and underscores that, while we may never step among the stars, we can perceive them, comprehend them, and expand our influence through knowledge and exploration. Within this boundary lies the measure of our species, limited in presence, bound by biology, yet capable of transcending space through curiosity, intellect, and technology, defining humanity's role in a universe that is vast, indifferent, and endlessly inspiring. As we drift back from the edges of the solar system and the distant Oort Cloud, let yourself relax, knowing that even though human presence is limited, the universe continues to unfold its mysteries before you. The stars above, the signals that reach across light years, and the robotic explorers venturing where we cannot, all remind us of the incredible reach of curiosity and knowledge. Tonight, as you lay your head down, imagine the vastness of space, the silent dance of planets and stars, and the small, precious sphere where humans exist. Let the understanding of our limits bring calm rather than fear, a sense of wonder rather than frustration. Our bodies may be bound to the inner solar system, but our minds, our imagination, and our dreams travel far beyond, exploring, observing, and marveling at the cosmos. Allow yourself to drift into sleep with the thought that the universe is enormous, timeless, and beautiful, and that even in our small corner we have already achieved the extraordinary. Every heartbeat, every breath, every thought connects you to the cosmos, and though we may never walk among the stars, we can know them, measure them, and feel their vastness in the quiet of the night. Sleep now, carried by the knowledge that curiosity and wonder transcend distance, that the farthest humans could ever travel is still just a beginning for your mind, and that the universe, infinite and serene, continues to unfold around you as you drift into the comfort of dreams.